Hey everyone, and welcome to this explainer. Today, we are looking at the absolute bleeding edge of automotive functional safety. We're going to unpack a super complex, highly critical failure mode in hybrid dual motor systems, specifically the traction motor and generator motor, or TM/GM, torque coordination failure. So why does this actually matter? Well, in a hybrid transmission, like an eCVT, these two motors have to perfectly coordinate their torque in the microsecond domain. I mean, they're balancing engine starts, damping vibrations, managing regenerative braking, the whole shebang. If that coordination fails, it becomes an ASIL D level threat. That's literally the highest automotive safety integrity level there is. We're talking about a sudden loss of vehicle stability at highway speeds, massive high voltage spikes, or worst case scenario, unintended violent wheel lockup. This explainer is going to decode exactly how this happens, and more importantly, how modern engineering stops it in its tracks. So picture this. A catastrophic physical failure is starting deep inside your vehicle's transmission. You have exactly 60 milliseconds. That's the ticking clock. In functional safety terms, we call this the fault-tolerant time interval, or FTTI. 60 milliseconds. That's like, what, a fifth of the time it takes you to blink your eye? In that tiny window, the system has to detect an anomaly, diagnose it, and physically neutralize the threat before violent torsional resonance literally rips the gears apart or sends uncontrolled high-voltage surges right into the battery. It is, quite literally, a race against time.
Okay, here's how we're going to break this down. First, the anatomy of the torque failure, then the architecture and diagnostic system, DFMEA, design prevention, PFMEA, process controls, and finally, production validation. All right, part one, anatomy of torque failure, or the 4 dimensions of breakdown. To solve a problem, you really have to understand the pathology of the disease first, right? In these high-dynamic hybrid environments, TM/GM torque coordination doesn't just fail for one single reason. It's usually a breakdown across 4 distinct dimensions. Let's break them down. First up, torsional resonance. When motors and engines physically connect via planetary gears, sudden torque changes cause these microelastic deformations. The system uses active damping to suppress this, but if the software gets a phase lag greater than 90 degrees, that damping actually amplifies the vibration. It's exactly like pushing someone on a swing at the exact wrong time. Second, inductance mismatch. During extreme acceleration, immense magnetic flux forces the motor's iron core into deep saturation, and the actual inductance drops by 30 to 50%. If the control system is just using fixed nominal values, well, the motor outputs the wrong torque. Third is CAN-FD desync. Modern silicon carbide switches are wild. They turn on and off so violently, over 10 kilovolts per microsecond, that they create massive electromagnetic noise. That noise can actually corrupt communication frames and freeze torque commands. And finally, data tearing. Inside the processor, different cores run the traction and generator motors. If they try to read and write shared data at the same time without strict rules, it's literally like trying to read a page while someone else is aggressively erasing and rewriting it. Instant loss of sync. Moving right along to Section 2, Architecture and Diagnostic System, the vehicle's immune system. Knowing those 4 fatal threats are out there, engineers built a multi-layered immune system to neutralize them within that crucial 60-millisecond window. The first line of defense is something called plausibility gating. Think of it as the system double-checking its own math in real time. On one hand, the software calculates the estimated AC electromagnetic power coming from both motors. On the other hand, it measures the physical DC power directly from the high-voltage bus. It's constantly comparing these two. If there's a mismatch of more than 15% and it lasts for just 10 little milliseconds, the system instantly knows something is fundamentally wrong and flags a severe DTC P0A7A error. But here's a fun question for you. How do you monitor the brain that's doing the monitoring? You use an asymmetric dual-core lockstep setup. It's brilliantly set up as the doer and the checker. The main core is the doer. It handles the complex math, the motor control, the active damping. Meanwhile, the safety core is the checker. It's an independent safety manager that relies on super robust, simplified physical laws to verify what the doer is up to. If the checker sees the doer is about to breach safe power limits, bam! It forcefully bypasses the main software and shuts down the motor drives in under 100 microseconds. So the crucial point here is what actually happens after a severe fault is detected. The system executes an adaptive fallback strategy. It doesn't just pull the plug. Doing that could literally shatter the transmission. For minor deviations, it uses a smooth torque ramp down, fading power nicely at 1,000 Newton meters per second. But for a severe loss of control at high speeds, it triggers an ASC, active short circuit.
Now, this is a violent but totally necessary two-stage internal short circuit that magnetically locks the motors, clamping the DC voltage below 720 volts. This stops an uncontrolled power surge from blowing up the battery. But at low speeds, it uses AOC, active open circuit or freewheeling. It does this so it doesn't accidentally lock up the wheels and send you into a skid. Pretty smart, right?
All right, Section 3, DFMEA, Design Prevention Controls, or editing the engineering DNA.
Catching a failure in 60 milliseconds is awesome, but preventing it from ever happening is even better. And this really illustrates how deep the engineering goes. To stop that torsional resonance we talked about, engineers program virtual Kalman shaft observers to predict shaft twisting, giving us over 20 decibels of active damping. To eliminate data tearing between the cores, they mandate lock-free double buffering. Remember that inductance mismatch? They fix it by baking a massive 2D lookup table directly into the software, constantly adjusting for magnetic saturation to keep torque error under a tiny 3%. And to fight that crazy electromagnetic noise, they use split termination circuits with ultra-stable C0G ceramic capacitors to reject high-frequency interference.
Let's shift to Section 4, PFMEA, Manufacturing Process Controls, the factory floor defenses.
Because, let's be real, the best design in the world is totally useless if it's built wrong on the assembly line. The tolerance for error on the factory floor is razor thin, just 5%. During manufacturing, the circuit boards undergo 100% 3D X-ray inspections. The strict, unbreakable rule is there can be no more than a 5% total voiding rate in the solder joints of the microprocessors. That basically means tiny air bubbles. Why so strict? Well, because under constant road vibration and extreme temperature swings, those microbubbles turn into microcracks. And those cracks cause intermittent data loss and sudden torque failure at highway speeds. No thank you.
And before a unit ever leaves the factory, it faces the end-of-line, or EOL tests. One absolutely critical step is rotor zero position learning. The system dynamically spins the motors to calibrate their exact magnetic zero points. If this calibration fails to write perfectly to the flash memory, the factory's manufacturing execution system triggers a hard lock. It literally physically prevents the barcode from being printed, blocking the unit from shipping whatsoever. On top of that, these tests ensure that torque coordination delays never exceed 10 milliseconds and active damping overshoot stays safely under 5 Newton meters. Finally, Section 5, Production Validation and Testing, the ultimate stress test. We've designed it, we've built it, now we try to completely break it. The sheer brutality of this testing matrix is unbelievable. First, they subject the system to immense 3-axis random vibrations while swinging the temperature from -40 to a scorching positive 125 degrees Celsius for over 1,000 hours. The electrical resistance across the joints can increase by more than 1.2 milliohms. Next, electromagnetic immunity. They run the motors at a screaming 12,000 RPM while blasting them with intense electromagnetic radiation to prove absolutely zero data frames are dropped. Finally, they use high-fidelity hardware-in-the-loop simulators to inject catastrophic virtual faults, like violently disconnecting the high-voltage battery under full load. The system has to recognize the fault and successfully execute its active short-circuit fallback, clamping the voltage, all within that magic 60-millisecond window. Which brings us to the edge of tomorrow. We have engineered some truly incredible safeguards to master this complex dance between two immensely powerful electric motors. But the arms race never really stops, does it? As EV motors push well past 12,000 RPM and silicon carbide switching frequencies soar to brand new heights, everything happens faster, and that margin for error just keeps shrinking. So it really makes you wonder, as powertrains become even more dynamic, will 60 milliseconds soon be just too slow to save the system?